Okay, so this week we have 5 problems again. The first 2 are probably a little bit more straightforward, but we'll go through those. And then the last 3 have a bit of a theme. Maybe you don't know what the theme is yet if you haven't done it, but anyway, let's look at the problems. The first one, it's a warm-up problem. You have a bunch of strings, and you're supposed to sort them. The only thing that's different is that you only want to sort based on the first 2 letters of the name. Okay, so nothing else in the name is used for sorting. So if 2 names have the same first 2 letters, they should stay in the same order as the input. Then this is known as a stable sort. So stable sort basically means that if 2 things have a tied, then you want to sort the output based on the input, the ordering. Okay. Sorting is case sensitive based on ASCII order. So actually, if you just use the standard string comparison, it is this order. So you don't have to do anything else. Up to 500 test cases. Each case has up to 200 words. Each word has at least 2 letters, up to 20 letters. So why does it matter that you have at least 2 letters? Because otherwise you can't look at the first 2 letters if you have strings that are less than 2 characters long. And then you're going to sort them. Okay, so there's not too much to say. This is a sorting. Basically, you don't want to sort anything yourself. You want to use the built-in STL sorting algorithm. And the main thing to remember is that the STL sorting algorithm has 3 parameters. Well, there's 2 parameters for sure, which talks about the start and the end of where you want to sort, but also a third parameter, optional parameter, that says what you want to use to compare 2 items. In the normal case, you just use the less than operator for, let's say, strings, and it'll just compare using the less than operator by default. But in this case, we need to do something a little bit special. So we want to have a comparison that takes the 2 strings that I'm comparing, extract the first 2 letters, and then compare. Okay, so that's basically it. The only other problem is if you have the same 2 letters, you need to make sure that the orders are not switched. So what should we do, right? So if you have, I don't know, a string hello, and then a string, if this is S1, and S2 is, I don't know, world, then S1 dot substring 02. So this is the start of where you want to start the substring. This is the length, would be exactly the first 2 letters, right? So what you can do is just look for the substring of 2 letters, first 2 letters, and then compare. And whichever one is smaller, that one goes first. The problem comes when you have 2 that are the same, right? So if you have hello and help, then both of them have the same first 2 letters. We want to make sure that the order is exactly the same as what the order in the inputs. So at this point, you have 2 options. The first option is that when you read in the string, you don't store it as a string of, this is an array of string or vector of string. You store it as a pair of string and an int, where this string is, if you want, actually just the string, of course, whatever string you read in. And then this one is the index in the original array. And if you sort this first part and they're equal, then you compare the second part. So that's one way to do this. So you write a more complicated comparison function that compares pairs of strings and int. For first, you extract the string, extract the first 2 letters and see if they're the same. If they're different, then you can compare and return the results. If they're the same, then you got to compare the index. So that's one way. But the other way, just a lot easier, I guess, is to realize that in STL, there is in fact something called stable sort. This, oops, did I accidentally kill? Yeah, I need to move this out the way. So there is something called stable sort, which is exactly what we want to do. Okay, so let's just look at this. The main routine here, basically I just call solve as many times as I want, as there is input. I also pass in whether this is the first time solve is called, because in the output it says print a blank line between cases. You don't want a blank line before the first case. You don't want a blank line after the last case. So what I'm going to do is I'm going to print a blank line before any case, unless it's the first case. So I have to remember, is it the first time I see this? Then whilst solve tells me that there's another case, I just keep going, but also set false first to be false the next time. So what do I do here? I read in n, and if n is 0, I return false. There's no more inputs. Otherwise, I create a vector of n strings. And this is a way to, if I don't want to write a for loop with an integer index, this is one way to do this. I already have n objects. In my vectors already size n. So I just loop through all the elements in my vector. Remember to pass by reference, otherwise we won't change the items in the vector. And then just read it. If you don't like this, you can write a for loop, for I from 0 to n minus 1, c into v bracket I. That's the same, right? So you can write for ins I equal to 0, I less than n, I plus plus, c in vi. Okay, that's the same. If you want, you can also not declare a vector of size n, and then just keep on reading strings and calling pushback. But it's more efficient to allocate the size all in one go as opposed to resizing all the time. And then we call stable sort, which has 3 parameters: the start of the array of the vectors, n of the vector, and then the comparison operator, a comparison function. And then here, I print a blank line if it's not the first time, and then here I just print out all the entries in the vector. So how do I do the compare? I look up the first prefix, I look up the second prefix, and I just compare. If the prefix 1 is less than prefix 2, I return true, otherwise I return false. That's a pretty standard sorting comparison function. You return true whenever the first argument is less than the second argument, and that's the only time you return true. Okay, so this problem should be pretty standard, but of course, how you do it and how fast you do it it's part of the process. And then, of course, if you know about this stable sort, then everything becomes a lot easier, I guess. Okay, now let's look at the next problem. Okay, hot light. So you have an array of up to 50 integers. Each integer is between minus 20 and 40. And you want to figure out the best day to start your trip and the maximum temperature during the 2 hiking days. If there are multiple choices that minimize the value of t, I'll put the smallest day. So first day that works. What is this? This is the idea is that you have a 3-day trip. So you have a 3-day trip. The first day you go up, the second day you stay at the top, and the third day you come down. So you want to minimize the maximum temperature during the 2 hiking days. So basically, in a sequence of 3, so if I have A0, A1, A2, these are the numbers. In a sequence of 3, I don't care about the one in the middle. I only care about the start and the end, because I go up on the start and at the end I go down. And then out of these two, I want to take the maximum of the two, because it's the maximum temperature of the 2 days. And that would be the temperature for that trip if I start on day 0. If I start on day 1, then the temperature, it's the maximum of the day going up, which is A1, and the day going down, which is A3. And I just keep going, and I want to find the day where the TI is minimized. And if there are multiple TIs that are minimum, I pick the first one. Okay? And because this is only, and it's only 50, you can just try them all. There's not really any issue with, the complexity and runtime and all that stuff. So we'll just get straight to it. So you read an N, and I read in the temperature N of them. And then I have these 2 variables that keep track of what is the best temperature and what day is the best to start. I set the temperature to be the maximum possible integer, because I guess any temperature that I find will be better, and it will automatically override that. Okay, so what do? I check the I is my starting date, and I have to make sure that I don't go out of bounds. So the way that I look at this is, if I start at day I, then the temperature that I'm looking at is temp at I and temp at I plus 2. So I plus 2 is the largest index that I have to use. So I just make sure that the largest index I have to use is still in bounds. Okay, so that's the way that I like to think about this, to make sure that I go to exactly the right spot, but not too far and not too early. So here I just look through all the starting dates. I look at the temperature of the first day and the third day, take the maximum, and that's the temperature of that trip. If the temperature of that trip is better than the best I have so far, and the very first one will automatically be less than ins max. So if I find a better one, then I remember the day that I found this best temperature, I will update the best temperature. Now notice that I use less than instead of less than or equal to. If I use less than, it means that I will only update this the very first time I find something that's better. But every other time I find something that's just as good, I will ignore it. Right? So that makes sure that you pick the first one when there are a bunch of ties. If you want to pick the last one when there's a bunch of ties, you change it to less than or equal. So every time there's an equal, you will replace the old one. So you'll just keep picking the furthest, the last one that has the same minimum temperature. Okay, so those 2 are the warm-up problems. They're not hopefully too hard. And let's look at something that may be a little bit harder. Okay, so in this case, you have 100 cases. It doesn't matter how many cases you have. We'll just look at one case at a time. You have 20, up to 20 positions. These are the shops, and the positions are between 0 and 99. There is nothing, okay, nothing that says that these positions are distinct, okay? So you just have to remember that. And then you want to park in a place that is optimal, that allows you to go to every store that you want to hit and come back to the car, of course. Okay, and then he's very strong and does not mind carrying all the bags around. So you don't have to go to a store, come back to the car to drop things off, go to another store, come back to the car. You just go, start from the car where you park the car, go to everywhere that you think you need to go, and then go back to the car at the end. Okay, so we have a number line, and then you have certain shops that you want to go to. And now there's nothing that says these shops can be distinct, so we will allow for the possibility of non-distinct places. So some places might show up 3 times, whatever. Okay. Actually, let me just make sure, does it say that everything is distinct? Blah, blah, blah. No, they don't say that, so then you don't, if they don't say that, you can't assume it. Okay, actually, it doesn't really matter. All right, so if you were to park, doesn't matter where you park. So let's say that you decide to park here. Now, how far do you have to go? Well, you're going to have to visit the leftmost one at some point, and you're going to have to visit the rightmost one at some point. And so it's better, let's say if you want to visit the leftmost one first, there's no reason to stop in the middle and double back. You might as well just go all the way to one side, right? Because it's doubling back, just add to your distance, and you can carry as many bags as you want, so you don't need to go back. You can then, at some point, you have to go all the way to the rightmost. Again, it doesn't help if you're, when you hit the ones that are not the rightmost, to double back. So basically, the only thing that matters are the extreme ones. And the question is, do you go to the leftmost one first, or do you go to the rightmost one first? Okay, and then eventually you have to come back here. So either you go to the leftmost one first or the rightmost one first. Those are the only 2 options, really, that minimize that. Now the question is, where should I park? Okay. Should I, or maybe I should, what about if I park actually over here or over there? Why do I have to park between 0 and 99? Is there some, did it say anything about I have to? It just says that all positions are integers. It doesn't say that, it says that the positions on the long street for the shops are between 0 and 99, but it doesn't say you have to park between 0 and 99. So it's also possible that you park somewhere else. And in that case, let's say you park really far on the left, then you might as well sweep all the way and double back like this. Okay? And then if you're parking really far on the right, then you sweep all the way to the leftmost, and so on. Okay, so let's call these positions A, B, and C. And let's call it, I don't know, min and max. Min and max shops. If I do position A, so if I park to the left of everybody, then the total is, basically I have to go from max minus A times 2, because I have to go all the way to the max and come back. If I park at position C, then I have to go C minus min times 2. Now, already, if I have to double back, from A, go all the way to max, and double back, then actually I can get better results just by moving this way. If I move my A closer to the leftmost point, I would get better. And I can always get better results until I get to this point. So basically, if you are parking left of the leftmost one, you can get better result by just moving to the leftmost one. And similarly, if you're parking to the right of the rightmost one, you can get a better result by parking the rightmost one, because you can reduce C, for example, which will reduce C minus min. So basically, what I'm saying is there is no reason to not park between A and B, min and max. So we'll ignore this line of thought. So now we've decided that we're gonna park B somewhere between A and min and max, but it could be min or it could be max. We don't know yet. Okay, if we go leftmost first, we first have to go from B to minus min. So we go leftmost first, we go this way. Then we go all the way to the maximum. And then we go all the way back to the car. And we try to figure out what's going on. We have two max. So we collect the two maxes minus two min. And this B and the minus B cancels out. So the weird thing is that it actually doesn't matter where you decide to park your car, no matter what B is, the cost, it's always the same, as long as you park in between min and max. It's a little bit counterintuitive. And you can work out the same thing if you were to do the rightmost first, which I'll leave it to you to figure out. But once you figure it out, the code is really easy. Okay, so this part just goes through the number of cases and solve it each case. And then here, right, reading the position, so I use the same trick. And then I just ask, what is the minimum element? What is the maximum element? And the answer is 2 times max minus min. So we start with thinking, what if we don't know what B is? We try to, where we park this car, we try to work out the expression, but then somehow it turns out that it doesn't actually matter. So that makes it a little bit easier once you work that out. Okay, the last two problems are sort of the theme problem this week. So here, I have a bunch of milestones. It says that you have a bunch of milestones spaced a kilometer and a half apart. Actually, the kilometer and a half doesn't really matter because everything else later on, it's miles. So there were milestones intended to demarcate this van der Waals unit of measurement. So being so old and blah, blah, blah. So not all of these stones have remained. Passing by some more of these tethered markers at a constant but unknown speed, you may still be able to gain some information from their placement. For example, since you started counting, you have passed exactly m remaining stones. How fast could you have been traveling? Okay, the first line contains m and n. Up to 1,000, m is the number of consecutive stones you noticed, and n is the total number of stones along the road, respectively. One line containing m, distinct non-negative integers t1 through m, as in ascending order the times at which you pass stones in hours. And notice that these are up to 10 to the 15, so you need 64-bit integers. And then one line containing n distinct non-negative integers xi's in ascending order, which are distances along the roads for each milestones. Again, these are up to 10 to 15. Output two lines. First, the number of distinct possible speeds at which the car could have been traveling. And second, a space-separate list of all the possible distances between the first milestone you saw and the second milestone you saw in increasing order. Okay, so what is going on? So here we have 4. These are the times. And then these are the distances of the stones. Okay, so let's look at this. 1, 2, 4, 5. So the times are 1, 2, 4, 5, and then 6, 8. I wonder if copy and paste will work in my whiteboard. Probably not. Oh, sort of copy. Okay. All right, so I have 6, 8, 12, 18, 26, 28, 30, 34, 36, 37, 39, 40. Okay, so that's what we have. Oh, I'm not allowed to erase that. Okay, well, whatever. So the idea is that 1, 2, 4, and 5 refers to the time that you see 4 consecutive milestones. So maybe these 4, maybe these 4, maybe these 4, or these 4, etc. We don't know which one. And so, for example, if we look at this one, okay, so let's write it down again. At time 1, 2, 4, and 5, at distance is this. So from here to here, time is 1 and distance is 2. So the speed, it's 2 over 1. Okay, well, in this case, it's divisible, so just 2, but in general, it might not be divisible. Here, the distance is 4, time is 2, so it's 4 over 2, but again, it's 2 over 1. And then here, the distance is 6, but the time is 1. So in this here, the speeds are different. If the speeds are different, and because we said that we are going at a constant speed, you could not have been able to observe these 4 because the speeds required are different. Okay, what about the next one? So 1, 2, 4, 5, 8, 12, 18, 16, 26, sorry. So here, the distance here and the speed is 4 over 1. The speed here is 6 over 2. So already this is no good. So that's no good either. What about the third one? 1, 2, 4, 5, 12, 18, 26, 28. This is 6. This is 2. That's no good either. Okay, so we have to keep looking. We look at this one. That's no good. Which one it's possible? This one is possible, I think. So let's try 1, 2, 4, 5, 28, 30, 34, and 36. So this is 2 over 1, distance of 2 and time of 1, 4 over 2, which is the same as 2 over 1, and then 2 over 1. So this speed is possible, and the distance between the first and the second marker is 2. So 2, and then apparently there's a 1. So the 2 possible speeds, we found one of them, which gives the answer 2. And what about the 1? With the 1, where does it come from? It comes from the last one. So here, hang on, it's my audio proper. So here, this is 1 over 1. This is also 1 over 1. And this is 2 over 2, which is also 1 over 1. So that's another speed that works. Now, why do I write 1 over 1 and 2 over 2 as opposed to just 1 and 2? Because you can get situations where the denominator, it's not does not divide evenly into the numerator. And so you have to worry about that too. And in fact, you have to worry about keeping track of exact fractions. So what is going on? What is going on is that basically you're going to have to try each chunk of m consecutive milestones. And for each one, you check the speed. If they're all the same, then that's one possibility. And you want to put all of them, okay? Also, there could be multiple chunks that are okay, but they all have the same speed, in which case you have to report only one of them. Okay, so when you collect the speeds, you have to make sure that you don't collect duplicates, or at least have some way of removing the duplicates. Okay, so the code, it's here. So first I read in the time and the x values, and remember that I'm using 64-bit integers, so that's very important. Then I'm going to have a fraction class that I'll show you up there later. I have my fraction class that remembers all the possible speeds. I use a set because I don't want duplicates. And similarly, the distance I want to print in the second line, again, it's also a set. So here, for every, so this basically just checks all the m. I slide the window of m milestones across. I is basically start of the window, and I use the same trick here. If I is the start of the window, I plus m minus 1 is the last item in the window, I make sure that it's not going to go out of bounds. The fraction, the speed, is just the distance at the I starts, I plus 1 spot minus xi, and then divided by the time of 1 minus times 0. I have some debugging statements here that I didn't bother removing. And then I'm just going to assume that everything in the window is true. It's the same. And for each one, for each of the subsequent, when I look at the second speed, and if the speed is not the speed 2, the next speed is not the same as the speed that I have at the beginning, then I have false. Then I know that I don't have the same anymore. If at the end of all this, speed is still the same, I insert this into my set, which is a possible speed, and then the distance that triggered that speed. And then at the end, I just print out how many speeds there are in my set, and then I'll put all my distances. So the fraction class, we actually have that in the code library, but you don't, I wrote it myself, doesn't really matter. So it's a fraction class, but I use a struct, so everything's public. So there's a numerator and denominator. So I initialize, you tell me what the numerator and denominator is. I initialize the numerator, denominator, compute a GCD, and divide by the GCD to get rid of the common factors. And if they are always, and then also in this case, fractions, the fractions I have don't have negative numbers, so I don't have to worry about whether the denominator is negative. I just don't care about that for this problem. And to know if two fractions are the same, because I always remove the lowest common factors, then it's the same as just checking if the numerator and denominator are the same. The not equals is just the opposite of equals. Why do I need not equals? Because I use not equals here. I also need a less than operator because I'm using a set, and set requires the things that I put in a sort. It's comparable because the internal is a binary search tree. And the way that you know if n1 over d1 is less than n2 over d2, is to cross multiply. And that way you don't have to worry about floating point computations. Okay, And this works as long as the denominators are positive, and you don't have to worry about negative in this problem, so that all works. Okay, so this is a little bit of a, so what is the theme here? The theme here is that we're doing a bit of a search. We're trying different things, and then we're trying to figure out what is the best one. Or we're trying all the possibilities and collecting the answers. Okay, the last one is the one that's perhaps the most involved. So you have this monk, and it goes up in a certain time, and then it comes down and then it comes down in the trip, and then you have to try to figure out at what time are they in the two trips, are they the same? So let me just draw a picture. If you haven't read the problem, you should probably read the problem first. So you have time, and then you have height. So the monk on the way up will go something like, they'll tell you that from a certain time to a certain, they'll give you these checkpoints, these segments, and then in each segment, they'll tell you how wide the time is and also how much you have gone up. And within that segment, you go up in a straight line, in a constant speed. Okay, so you go like this, and then maybe the next time you go a little bit less, maybe even don't move for a while, and then maybe you go really hard, and then you go a little bit less, and then go like this. Who knows? Maybe something like that. And then on the way down, you will also be given time steps, which may be different time steps. Okay, they don't have to be the same times. And you start from the top. So whatever the total height you've gone up, it's where you start off. And maybe you go like this. Okay, so maybe that could give you, they don't even have to start or end at the same time. And your goal is to find the first place a time on both trips where they are the same height. Okay, so that's the question. So there are two ways you can do this. But first way you can say is, well, it doesn't matter whether you're looking at green path or the red path. Each path is a bunch of line segments. So I'm going to look at all possible green line segments. I'm going to look at all possible red line segments, and I'm just going to intersect them and see if they intersect. If they do, I got my answer. If not, then I try a different segment. So maybe I have a line segment like this. Maybe I have a line segment like here. And these two line segments do not intersect. But if you're not careful, you might think, if you're using, I don't know, some kind of equation of a line, you might think that they intersect because this equation of a line eventually will intersect. So what you have to do, let's call it, let's call it T1 and T2, heights 1 and heights 2. The equation of this line would be height equals to what? So T is in between. Height 1 plus the slope, which is h2 minus h1, t2 minus t1, and then times t minus t1. That would be the heights here, if time is between t1 and t2. So you have to make sure that. And you can form a similar, so this is t3 and t4, and this is height 3 and height 4. You can form a similar equation Now this all works because h4 is actually less than h3 here, so this slope is negative. And then you would say, well, if the height has to be the same, this height and this height have to be the same. So you set the two right-hand side to be the same as each other, and then you solve for t. And you solve for t, you can have many things that can happen. Maybe you cannot solve for t because you need to divide by 0 at some point, and then there's no solution because there are two parallel lines, for example. Or you solve for t, but then the value of t, so remember that t has to be between t3 and t4, and the value of t is not between here or not between here. In that case, it's, it's not possible. So that's one way to do this. And the code is kind of here. I have a pair of integers. Well, anyway, you can look up I even have some comments about how to do this intersection, and then I solve one. So for each line segment of the ascending phase, I call find time, which goes through the descending phase and then just intersect. And if I find an intersection that it's in the range, then I can return it. Otherwise, if I can't, at the end, I return -1. Okay, so you can, if you want, you can read through it. You can try all possible pairs of line segments. They're only up to 1,000 or 5,000 segments each way. So 5,000 squares, what is it, 25 million, which is not that bad. Okay, that you can of course do. But I want to show you a completely different way of looking at this. Let me erase all of this stuff. Now, what we're looking for is the time where we intersect. What do we know about the green line and what do we know about the red line? The green line, it's climbing this hill. Okay, so as I move from left to right, it goes up. It might just stay this flat for a while, but it will never go down. The red one, on the other hand, as you go from left to right, it goes down. Okay. Now, the other thing is, instead of saying, well, let's just solve for this line intersection or whatever, let's change the problem a little bit. If I give you a time, whatever time it might be, so I tell you the time, and I ask you, can you tell me at this time what is the green path, the height, and what is the red one? Well, what you can do is you can just go through the segments, find the segment where t belongs, okay, and then use that formula. Use that formula that I showed you, substitute t into there, and then you can figure out the height. Okay. Why is that useful? If you can just figure out the height of each of these paths, given particular time, you can look up, for example, let's pick a random time. Now we already pick a time. So let's say we pick a time. We know that the green one, it's bigger than the red one. The height on the green one is bigger than the red one. We know that the green one can only go further up, and the red one can only go further down. So if the green one is already above h, can they cross ever again? No. That means the answer that you're looking for is not over here. This t is already too late. What if you're on the other side, right? So if you're here, if you look at this, and the green one, it's less than the red one. So the red one is still higher. that means that the answer cannot be on this side, must be on the other side. With that in mind, what we're going to do is we're basically just going to say, we don't know what the answer is originally. The answer might be here, as low as 0, as high as the last spot. We don't know where it is. So take a step in the middle. And we ask red one, green one, which way is it? If they happen to be the same, you're done, right? Well, actually, you don't know that because they could be the same at multiple places. They could both be flat. So you don't, but you know that if the green one is bigger than the red one, for sure, the answer is to the left. And so what you can do is you can cross out all the things to the left of mid by resetting this to high, and then just keep continuing by dividing things by 2. If, on the other hand, the green one is less than h, you know the answer is to the right. So you update low to high. Update low to mid. The only tricky thing is what happens if you have if both of them happens to be flat at the same point. So you might see that they're the same, but actually you want to be at the first spot where they cross each other. And you can fix this by saying that if the green one is greater than or equal, then move to the other side, then move to the left. So if they're equal, that may or may not be the answer you want. For sure, the answer is not to the right. So you just move to the left and see if they're more equal ones. And basically what you do is you keep narrowing low and high until low and high are so close together that whatever number you choose is going to be within the digit of accuracy that you asked to produce. So here they ask you to produce up to 5 digits of accuracy. So you just basically do this keep cutting this interval between low and high in half until it is the gap between the two is less than 10 to the minus 5. So my second one, I have a second solve here. So I've simulate. This just says you tell me which path you want to simulate. So this is a bunch of points. Points are time and height. Time and height, yeah. And then what time you want to simulate, and I just go through all the segments and ask if the time that you give me is between the 2 times of this segment, then I would apply the formula. Okay. I have to be a little bit careful because these are integers, so I have to convert to doubles, otherwise I have an integer division. But anyway, basically I simulate it. And then I basically do a binary search. So lowest 0, highest the minimum of the largest time of either one, either path. And then while the distance between low and high is bigger than 10 to the minus 8, I usually, 10 to the minus 5 is what they ask for. I usually put a few extra digits just in case, because when you divide things by half, it gets to the bottom so quickly anyway, it doesn't really matter. So mid is low plus high over 2. I simulate the up path to see where the height is for the up one. Figure out the height for the down one. If up is less than down, that means that I haven't reached it yet. So I set low to be mid, otherwise I set high to be mid. There's some other code, to deal with inputs and so on, but if you get to this problem, you can probably figure out how I do the input, or you can figure that out yourself. So here, I guess the lesson is that you have the answer that you want is a time, and then the question is, can we do a search on the time? Like if somebody tells you what the answer is, can you easily figure out whether that answer is good or not? Okay. So I think that's definitely a different kind of I guess, problem solving strategies that you may not have seen. And so I want to introduce this to you. And definitely, if you have time, try this because it will be quite useful technique to have. All right, so I'll stop here and then put up another set next week.